Hello, so my name's Ethan.
I'm Michael.
We're here to present our Communicator certificate on Module 8, and we did the option 1 problem. So, to get into things, the task for this problem was to design a firewall and demonstrate that it meets the New York State Building Code standards. Um, so the objective, using New York State Building Code standards and the semi-infinite solid equation, design a firewall with a certain material and thickness that is capable of adhering to New York State building fire codes. So to do this, we did some research on the fire codes, which we'll get into later, as well as made some assumptions that you will see in the following slides. So to start off with some background on what a firewall is. So the purpose of a firewall is basically to separate two areas. You're typically separating an area that is prone to fires or is containing materials that are highly combustible or dangerous. So there are many uses. The use in the picture here um, we have high voltage areas in a electric grid. So this is just protecting other areas in case one of these explodes or causes a fire or whatnot. Other uses would be for storage if you're storing highly flammable materials, or just to separate areas such as a garage from the house to protect areas in the event of a fire.
Okay, so the material we used for our firewall was concrete. Some of the properties that we found for a concrete firewall were a thermal heat capacity of 880 joules per kilogram Kelvin. The thermal conductivity of concrete is 1.4 watts per meter Kelvin, and the density of concrete is 2,300 kilograms per meter square cubed. For our state fire codes, we use the ASTM E119 manual. And we found a heat flux for auto ignition of wood, which is 12,500 watts per meter squared. The minimum thickness when exposed to a heat flux for 2 hours would be 1.127 meters, and this would be for a maximum temperature of 1010 degrees Celsius.
And we'll also have to withstand this for 4 hours or 7,200 seconds. So some assumptions that we made when we were solving this problem, one of them was that the conduction was one-dimensional. For this case, we only looked at the x direction and not negating the y and z directions. We also assumed it was a semi-infinite median. We neglected radiation and convection, and also assumed all properties were constant throughout. Also, for the design, we did assume some dimensions of this firewall. We assumed that the thickness of the wall was 0.25 meters. So basically, we're going to test to see if this thickness would work later on in the problem. And we chose an initial temperature of the wall to be 25 degrees Celsius.
Okay, so for the analysis, um, in this case of transient conduction, we had to use a special case for heat flux directed towards a semi-infinite solid. And once we found our value for temperature, we would then check to see if the thickness was suitable that we chose in the beginning for the fire code specified. Um, at the bottom right here, you see a preliminary drawing of our firewall. Note that the initial temperature of the firewall and the thickness of the firewall have been changed. The initial temperature we have is 20. We changed that to 25 degrees Celsius, and the thickness of 0.3 meters was changed in our final solution to 0.25 meters.
So to start, we calculated alpha using the material properties of concrete. Um, so yeah, alpha is equal to the thermal conductivity over the density times the heat constant. And for this case, alpha for concrete was 6.9 times 10 to the negative 7.
So, using the heat flux on a semi-infinite solid case for transient conduction, from lecture 19, equation 5.62, here is the temperature value at a specific point within the semi-infinite solid at a particular time. Checking for the front side temperature, x becomes 0, so this simplifies the equation down, and we found after the simplification that the approximate front side temperature was 731 degrees Celsius. And here is a picture on the right of this case 2 using heat flux on a semi-infinite surface, just to note. Yes, so checking for the thermal penetration depth. To make sure that our wall was suitable and we had a high enough thickness, we used the thermal penetration equation from lecture 19. This equation is 2.3 times alpha, or alpha times the time over 1/2, or alpha times time squared, or square root of alpha times time. So the time that we used was 2 hours. This equates to 7,200 seconds. And we found from our calculation that 0.1623 meters was our thermal penetration depth, which is less than 0.25 meters. That was our chosen wall thickness for the firewall.
So in conclusion, we kind of compared our calculations to what the requirements were. Like we said, the final surface temperature that our wall would experience is 731 degrees Celsius. And this is an acceptable value since the code said that it would have to be less than the maximum value of 1010 degrees Celsius. So in terms of the temperature, it is good. And in terms of the thickness, we determined that the heat would penetrate a thickness of 16 centimeters. So in order to make sure that this heat does not penetrate the wall completely, we had to make our thickness more than that. So we chose a thickness of 25 centimeters, just proving that this design is adequate to fulfill all the fire code in New York State.
As well as there being no influence from the backside thermal influence on the firewall as well.
But that's our presentation. Hope you enjoyed it
Thank you
and
for
learned a
listening.
lot.